Hi class, let's talk about exponential growth. If I'm looking at an item growing exponentially, A of t then would be my final amount at some time t in the future. This A, lowercase a, is my initial amount of the item that I had at the very beginning. And if it's growth, it will be a rate that's over 1. So it's 1 plus our rate of increase in decimal form. For example, if it's increasing by 3%, I'm going to think of that as, go over 2 places, 0.03 when I use it in my equation. So decay then, exponential decay, capital A of t is still my final amount after some time t has elapsed. Oh, that's my time t in both equations. And my little a in both equations is my initial amount. And this time you'll notice that it's 1 minus my rate. So this is because I'm decreasing. It'll be a number less than 1. This is my rate of decrease. Keep in mind that my r is in decimal form. I guess I should be more over here on growth. It's r that's in decimal form. So let's look up above at the do now. These are problems straight out of the Illustrative Mathematics Algebra 1 book. Not sure what material you were using for algebra last year, but let's take a look at these. I know, for example, since this rate is a number less than 1, this is decay. I know since this rate is something greater than 1, that equation is growth. I know since this is less than 1, I know it's decay. And I know since that's greater than 1 that this is growth. So, for example, if the initial amount of my bacteria is 150 and it's doubling, that's my entire rate. My entire rate is 2. That's my growth, if you will. That my amount at any time t is equal to my initial amount, which is 150, times 2, which is my rate, to some amount of time. So let's take a look at example 1 down here. It says the first year of a music festival had 100,000 people attend. That's my initial amount of people. That's going to be my A. The attendance increases, so I'm going to be adding by a rate of 8%. So I'm going to be using 0.08, that's 8% as a decimal. Write a function to model this situation. Well, the amount of people, so the amount of people at some time t is going to be equal to the initial amount of people, 100,000, times 1 plus 0.08, so 1.08 to some time t. That equation models it. So how many people will be attending by the 5th year, by year number 5? So by year number 5, when t is 5, I'm going to have 100,000 to the 1.08 to the 5th power. So remember, by PEMDAS, we have to do exponents before multiplication. So let's do 1.08 to the 5th power. And then let's multiply that by 100,000. And it looks like I'm going to say approximately. So the number on my calculator is 146,932.8. You can't really have 0.8 of a person. So we're going to round this up to 3. So I'm just going to take off my 0.8 and my 2, and I'm going to round up to my people, because we can't really have 0.8 of a person. Do you want to round down? Then you could round that down, and I'd be fine with that answer too. So let's take a look at example 2. The population of a city increases by 2% each year. The current population in the year 2017 is 315,000 people. Write a function to model this. So the amount of people at any time t is going to be equal to the initial amount times 1 plus my rate, which is 0.02 when I write as a decimal, so 1.02 to the t. And then when it says how many people will there be in 2025, well, from 2017 to 2025 is 8 years. So I want to know how many people there will be in 8 years. So when I fill this out, I put an 8 in for my exponent. And make sure on your calculators you're doing 1.02 to the 8th power and then multiplying by your 315,000. And I believe we get 369,072 people. Okay, so the next question, the annual rate of inflation, or increase in this case, as a decimal would be 0.038 over the next 10 years, which would be my time. The present cost of an oil change. So there is obviously probably a 1 missing from the front of this, or that should be like $83.95. It's not a very accurate number. It says write a function to model the situation. So again, the amount you're going to pay at some time will be the initial amount of $23.95 times then the increase 1 plus then 0.038 and then my time. So in this one, it says how much will it cost in 10 years? Well, we're going to insert that time t. So the amount that it's going to cost me in 10 years is the $23.95 times 1 plus 0.038, or just 1.038 to the 10th power. And I don't have the number in front of me, actually, for the answer for that. But just so you know, it's going to cost a lot more than that to have your oil changed in 10 years, I promise. Okay, you guys, let's flip to the next page. So sometimes we work with compounding money. So in this case, you'll notice that this equation looks a lot like the equation on the front, with the exception there is this new variable n that we see. So the principal is still my initial investment. My r is still my interest rate as a decimal. My time is still t, but now n is the number of times you compound it annually. So what does this mean? Well, if you compound it once or annually, that's 1 time a year. Your n is 1. If we compound it 4 times a year, my n is 4. If we compound something weekly, there's 52 weeks in a year. Daily would be 365, and monthly would be 12. And then semi-annually would be twice a year. So let's take a look at writing the equation for weekly. So to begin this equation, if I want to know how much money I'm going to have at some time t, then I need my initial amount, which was $5,000, times 1 plus my rate, which is 0.03 as a decimal. But this time it's divided by how many times it's compounded, which is weekly, so 52, to the exponent of 52 times my time. And they asked to find the balance after 10 years. So A of 10 is going to be 5,000 times 1 plus 0.03 divided by 52, and that's 52 times 10, or 520. So I will say part of this one is knowing how to put it into your calculator. The navy blue calculator students probably don't have an issue. You're going to put it in just like a sentence. But the classroom students, let me get a different color here. You're going to enter the 0.03 divided by 52 and add that to 1. Then you're going to raise it to the 520th power. Then you're going to multiply by 5,000. That's your PEMDAS, parentheses, then exponents, then multiplication division. I'm not going to do A, B, D, E, or F. You can work on those. All of your answers for A through F are going to be very close to each other numerically. The more it's compounded, the more money you make. So D really should be the largest number and A should be the smallest, but they're all going to be fairly close to each other, and you can check it in the filled in packet. Let's move on down and look at continuously. So this is something new for us. Sometimes something is, there's continuous growth. It's compounded continuously. It's decaying continuously. It's growing continuously. And we introduce this new special number, this lowercase e. Now I'd like to mention that it's an actual number. Oops, I apologize. It's an actual number. And just like pi is, for instance, it's like I in that it's not a variable, but like pi has an actual value, so does e. E has this value that's actually in your calculator. And so we're going to learn in the second set of notes in part 2 that I can use, that it's the inverse of natural log. That's how we can solve e equations. So in this particular equation, for this problem, my A of t would still be my initial investment of $5,000, but now there's no parentheses, there's no 1 plus or minus anything, there's this e, and then my exponent is my rate, which is my 0.03 times my time. So in this case, my A in 10 years equals 5,000 times e to the 0.03 times 10? So that would be 0.3. So to enter this in my calculator, if you're a classroom calculator person, you're going to do the 0.3 first. Then you're going to do the second button. And then you're going to touch our natural log button because the e is above natural log. That's why I have to do the second button. And then you're going to multiply by 5,000. If you're a classroom calculator student, you're going to do 5,000 times, and your e is on the left side of your calculator. It's also above natural log, so you're going to still have to use your second key, and then your exponent is going to be 0.3. And you should get, it looks like $6,749.29, which should be the highest yet. Thank you for watching, and I'll see you in class.